Okay, so for problem 3, we're given an uncharged capacitor, and we've connected it to a battery, and just before the instant that it sparks and the current runs through, we're supposed to find the potential difference across the capacitor. So for this problem, all we need to do is remember the equation that we learned, that delta V is equal to E and D. That means the electric field and the distance across the capacitor. So those two information are given to us directly. We know that the electric field is going to be 3e6, because that's given to us in the question, and that the separation distance is going to be 0.4 millimeters, so that translates into 0.0004. And if you calculate that out, you know your answer is just 1200 volts. Part B asks us to find the direction and the magnitude of the electric field in the resistor just before you see the spark. So we know that we're going to use the loop rule here, and we know that current runs through and it goes through, and around the loop it's just going to equal 0. So we can see, not current, I meant potential difference. So we know that the potential difference of the battery plus the potential difference of the resistor plus the potential difference of the capacitor is all going to equal 0. We know that from loop rule. Loop rule. Yay! So we know that the potential difference of the resistor is going to equal the negative potential difference of the battery and the capacitor. So we just use some of the formulas that we've learned, that delta V is equal to EL, so electricity of the resistor plus the length of the resistor is equal to the delta V of the battery plus the delta V of the capacitor. And we don't really need to translate these two, because we've already calculated the delta V of the capacitor right here, and the delta V of the battery is given to us. So now, if we solve for the electric field, we just get electric field is equal to all of this divided by L, which is going to be, electric field is 1 divided by 0.1 meters times 3200 volts minus 1200 volts. And you find that the electric field across the resistor is just equal to 20,000 newtons over coulomb. For the very last question, you're supposed to find the conventional current through the resistor. So for this question, what we have to keep in mind is that we have two different equations to find the delta V, which is equal to EL and IR. And those are equal to each other because we know that these two lead to the same thing. So if we set these two equal to each other, we can solve for I as EL over R. And we know that E is what we found in the part B, and L is given to us, and R is also given to us. So this becomes a simple plug-and-check question where you plug in these numbers and you get your answer of 5.714 amperes. Yay!